Today's topic, guys, is equilibrium. In equilibrium, what we're going to be looking at is processes. We take a look at these three bottles. One of these is not in equilibrium. Hopefully you can figure out which one it is. And we're going to discuss why that particular bottle is not in equilibrium. Two of the bottles are in equilibrium, and we'll notice some differences between the bottles. All right, bottle number one. Bottle number one we have is about 2/3 of the way full of water, 1/3 headspace, and we have no cap on the top. Second bottle is about half full. We notice that there's kind of like a condensate towards the top of the bottle. So 50% of that bottle capped is water and 50% is vaporous water. Last bottle that we have on the top also has a fog on the top of the bottle. If you take a look right there, we see the water droplets condensate, and we see that the bottle is the majority of it's full. I'd say it's about 90% liquid water and 10% gaseous water. Also has a cap on the top. Well, if you figured out which one is not in equilibrium, it is the one on the left side that does not have a cap. And that means that we have more of one process than another process. Well, what kind of process could be going on inside of the other two? Well, we take a look at the other two and we ask the question, where did the condensate come from? That's kind of easy to figure out, because we know that inside of each of these water bottles is a water cycle going on. A water cycle simply is we're going to have an equation that looks kind of like this. Evaporation must be taking place. So in the bottom of each of those containers, we have the liquid water is absorbing some heat, forming gaseous water. All right. In addition to that equation, we also have this equation going on where the gaseous water is forming liquid condensate, which, as you see, H2OL plus heat. That's the condensation. So in a sense, we have a water cycle going on in each of these two containers. We don't have that going on in the first container. We only have evaporation. Okay, so the rate of evaporation in this container on the left-hand side is dominating more than the rate of condensation, because all the gaseous water is leaving the container. It's just leaving, bye-bye. So we will never get the two rates to equal each other. In this container and this container, we notice that the two rates of condensation and evaporation are equal, not the concentrations, because as you can see, the concentration in the middle container is about, say, 50% liquid water and 50% gaseous water, whereas the last container, we have 90% liquid water and 10% gaseous water. So you can see the concentrations are not equal. But one thing we can say is that the concentrations are not changing. And the word that we use for not changing for concentration is constant. So how can we take a look at this and kind of merge this all together? We have this equation of evaporation and this equation of condensation. And if we wanted to kind of put it all together in terms of one equation that say both processes are happening, what we can say is H2O liquid plus heat makes H2O gas. Well, that's the same equation as we said before for evaporation, but notice the difference now. We have a second arrow. That second arrow is indicating to us that this reaction can go in reverse. So in this chapter, what we're going to basically look at, when we see a double arrow, it means that a reaction or a process is reversible. And we know that evaporation can be reversed very easily into condensation. We also know that freezing can be reversed very quickly into melting. There are two other types of equilibrium that exist called solution equilibrium and chemical equilibrium. Those we'll be able to see in our notes.